Hello, everybody. I would like to thank Pavel and Zbyněk for inviting me here. Also the beer is good, so I'm good. So, I will cover a little bit different aspect of autoscaling in this session. So the previous session was on the, let's say, cluster level, and also more like on the maybe technical deep dive. I would like to cover a little bit different, let's say, way of autoscaling or maybe type of autoscaling, which is more on the application level, and give you more like a highlights, maybe high-level overview, and maybe some tips. So my name is Zbyněk. Usually when I'm talking to English audience, I excuse for my name because it's very hard to pronounce for English speakers, but I suppose most of you here are able to do that, so that's good. So I'm maintainer of project KEDA, which does autoscaling Kubernetes. I'm with the project since the inception. I'm also founder of a company called Kedify, where we provide enterprise version of KEDA. I also worked before on project Knative, which also does a little bit on, let's say, autoscaling Kubernetes. I was part of the technical oversight committee. Okay, let's start. So I will cover like the typical stuff, why we should care about autoscaling. I will cover a bunch of different types of autoscaling of applications, and maybe talk about some challenges that we can face. So why we should do autoscaling? I believe Radek mentioned it in the previous talk quite nicely. This is like a long story, but basically you don't want to spend your time manually tuning your setup, especially if you're running on cloud, so you don't manage your Kubernetes instance, so you would like to autoscale to have the dynamicity. Why? If we look at this diagram, on the left-hand side, the yellow part represents the number of containers, so it's defined statically. So let's say we have 20 containers, and the red part represents the requests that are coming to the containers, or maybe the need for the actual autoscaling. So if we define resources statically, you can see that sometimes we are over-provisioned, sometimes we are under-provisioned. So this is bad UX, or we are spending a lot of money. If we enable autoscaling, we should ideally getting close to the diagram on the right-hand side, which is the state we would like to achieve. To achieve that, we need to configure autoscaling on both levels, on the cluster side and on the application side, because the application autoscaler is making the pressure on the cluster autoscaler to give us more nodes or reduce the number of nodes. So we should carefully configure both options. Yeah, this is maybe not PR, but from my experience over the years, the cost reduction could be very easily 30 to 40% if we configure autoscaling, carefully. Sometimes there were like extreme cases where it was like 60%. It was a company, they have like this asynchronous architecture around Kafka, and they had like a lot of microservices talking to this Kafka instance, and they were able to save more than 60% of the cloud cost, which is huge. The other aspect of autoscaling is performance, obviously. So autoscaling helps us to handle sudden traffic spikes. You can always over-provision and be, okay, I'm good, I'm safe. But sometimes there are like these sudden traffic spikes, especially if you are dealing with real-time traffic or very sensitive traffic to the delays. All right, so the autoscaling problem. We have our Kubernetes application, very typical one, deployed as a Kubernetes deployment. And this application is consuming messages from Kafka, probably using Streamzy. So we talk about autoscaling, why it is good. So let's autoscale this application, right? So the first naive approach would be, okay, let's use HPA, which is the default autoscaler on Kubernetes, right? So what HPA does, I believe most of you know, but I will just cover it for the clarity. So HPA monitors the utilization on the target deployment or the application and the utilization of CPU or memory. And based on that, it scales out the application. This is good, but if you think more about this specific use case, it might not be the best fit. I will cover this in a bit, but I will talk more about the resource-based autoscaling, which is the scaling based on CPU memory. So it's a very simple setup because it's built in Kubernetes by default. It's suitable for workloads with a stable, okay, there's a typo, with stable load on the workload. So it's good if you have like some stable load coming to the application, and you can easily scale out by the CPU consumption. It's a very good step, but it has a lot of limitations. Mainly, it's reactive, so it reacts to the actual problem that's happening. So your application is consuming a lot of resources, so it means it is having hard time to deal with the pressure. One aspect, you cannot scale to zero with HPA. So in order, if you would like to save a really good amount of money, you cannot scale the application to zero. One point about this. In this talk, we will be talking mostly about horizontal scaling. Horizontal scaling means that we are adding more replicas of the same application. Vertical autoscaling, on the other hand, is like we are resizing the application itself. Usually, the recommendation is to not mix HPA and VPA for the same workload, because if you think about it, HPA controls or monitors the CPU or memory utilization. Based on that, adds more replicas. VPA does exactly the same stuff, but it just resizes the application. So what you can end up with is basically that HPA will tell us to add more replicas. VPA will try to scale out the application. Actually, nomenclature here. If we are talking about horizontal scaling, we should use term scale out and scale in. If we are talking about vertical scaling, we should use scale up and down. This is usually mixed, but the language is clear about this. Okay, so this was the resource-based autoscaling, scaling based on the CPU memory consumption. If we are going back to our example, when we are consuming the data from Kafka, I think that what would be actually more clever is to scale out the application based on the number of unprocessed messages in the Kafka topic, for example. So in this case, if there are, for example, 1,000 unprocessed messages in the Kafka topic, let's scale out our application, give us more replicas, it will consume the data, and if there are no data, we can scale to zero. It's much better to reflect this kind of scaling through these metrics than through CPU or memory utilization, because CPU or memory utilization doesn't reflect the actual need for the scaling, based on the indirect metrics, or sometimes it's very delayed. So this is why we should consider using custom metrics, or more like event-driven approach, which is the Kafka example, for example. So with custom metrics autoscaling, it requires additional setup. So you cannot use just plain HPA. You need to plug a Prometheus adapter or use KEDA, which we talk a little bit later. But it gives us almost unlimited possibilities. If there are, so the rule is, if there are some metrics you can expose, you can use them for autoscaling. So it's very powerful setup, and it allows us to be more proactive. So the CPU memory consumption-based scaling was reactive, so it reacted to the actual load. But with this approach, we can be more proactive. Okay, so we can see, like, for example, these metrics in the, ingress. So let's start scaling out the target workloads before the load is actually happening there. With the custom metrics, the problem might be, or the concern might be, that it's not very real-time based, because usually we are fetching the metrics from some metric storage or some other solution. If we are getting the metrics, for example, Prometheus metrics from the target workload, we cannot scale to zero, because if we scale the workload to zero, we lose the source of metrics, so we cannot scale out again. The very similar setup is the event-driven autoscaling. I'm doing like this distinction because this doesn't depend on the custom metrics. It's more like for the asynchronous, let's say, environments and architectures. So, for example, architecture on Kafka, RabbitMQ, where we can access directly the queue length of, for example, Kafka topic and scale based on that. It's very powerful, and it allows us to really benefit from the asynchronous architecture. And it allows us to scale to zero. For example, if there are no messages in the Kafka topic, we can scale to zero completely, and then just scale out when we need. The second, or maybe the third type of, let's say, approaches in the scaling is I call it HTTP-based autoscaling. It's more like real-time scaling, when the application doesn't consume the data. Because in the previous examples, the application was responsible for the data delivery. So the Kafka client in the application was responsible for getting the actual data from Kafka. In this case, the data are being pushed to the application itself, so the HTTP traffic, typically. And the HTTP traffic is very sensitive to delays, so we should be careful about the scaling aspect, and we should start scaling out as soon as possible when the load is hitting there. So the HTTP-based scaling is more like a type of the custom metrics, but it's more like related to the real-time aspect of the whole problem. Because HTTP traffic is also an event, so we should be able to autoscale. As I told you, if there is a metric we can expose, let's use it for the autoscaling. The challenge is, The push versus pull model. This is what I just described before. In the previous examples, the application was responsible for pulling the data. In this case, we are pushing the data to the application. So we need to take into this consideration. For this kind of stuff actually to work, we need to have the metrics should be close to real time, as close as possible. We should think about like how to transfer the actual data. If we wouldn't like to scale to 0, for example, there are some other problems with gRPC, WebSockets, TLS, and etc. etc. But all of this is manageable. It's maybe a little bit more complex than the traditional approaches. These diagrams are just covered what I just mentioned. So on the left-hand side, there is resource-based autoscaling, so CPU memory. The red part represents the number of requests coming to our application, for example, and the blue line represents the number of pods, the replicas of our application. So it's reactive, so there is like this delay, so we are not able to handle the load properly. So for example, this example, a few weeks ago I talked to a very large bank. I cannot be more precise about the details, but they have like these microservices that were responsible for processing some microtransactions within the bank in some payment systems. They were using HPA and scale based on the CPU memory. They were very happy with it all the time because they gradually scaled out. But then there was some sudden traffic in the country because someone posted somewhere something, and there were a lot of users actually buying some stuff. So they needed to process a lot of transactions, and that was a problem because the HPA was reactive, so it was the scaling was delayed, and they had very big problems with this actually. So the better approach in this case is to get to the state which is on this side of the screen, where the number of pods are almost close to the number of requests that are coming there. So it reflects basically. So this is the state we would like to achieve. This is one of my examples we did, for example, with Trivago, if we are talking about HTTP scaling. So what they did before, they used Google Cloud Run, which is like a AWS Lambda. It's like a serverless. And they use it for scaling out developer preview environments. So if you think about Trivago platform, which is the booking platform, right? Every developer who develops a new feature there opens a pull request, and new copy of the application is deployed in there, full copy. And they have like a 200 or 300 open PRs simultaneously. And devs were using this kind of applications maybe a few minutes a day, and it was sitting there for weeks. So the spend was very huge. So they migrated to Cloud Run, Google Cloud Run, which is like this serverless offering, but the rest of the stack was on Kubernetes. And they were very happy with managing two different environments. So we developed a HTTP scaler for them that allows them to scale to 0 the preview environments on Kubernetes and have the similar capabilities. So for them it was a win because they just managed single Kubernetes environment, and they were able to save a lot of money because they just opened the PRs when they actually need them. The second case, I will just skip through it. It's very similar to the bank situation I talked before. This is like it's like a platform for students. When they enroll some exams, they create a lot of load to the application. So we help them with the HTTP scaling there to adjust the load. Okay, so this was the HTTP scaling. And then the third part, which is like let's say the newest part in the whole mix, is the AI, because AI is everywhere, right? There is a lot of buzz around AI. Everybody needs to be AI ready. So our example is still very same. So there is this guy making some requests. In this case, it could be like inferencing. So this guy is making some prompts, writing prompts to our model, and the model is trying to give me some good answer, right? So in this case, if we think about the AI workloads, we need to capture the incoming requests to measure them properly. So because it's similar to the HTTP-based scaling, right? And also the GPU aspect is very important here because GPUs are very expensive, as we know. So we would like to utilize them properly. So we should combine the HTTP-based metrics with the GPU metrics, so utilization, some kind of cache, etc., etc. So this is something that will be a hot topic for companies that would like to host models in their infrastructure. Because why? Because the compliance, for example, cost. They don't want to, send the data to OpenAI or whatever. And if they are already using Kubernetes, they would like to run those models on Kubernetes, right? So this is the thing we should really think about, like how to balance the throughput and the utilization. Because if I write the prompt, I would like to get the answer as soon as possible, right? But I don't want to spend $1 million on my AWS bill. There are some frameworks that helps with the serving part of the models on Kubernetes. One of them is VLLM, very good framework project. I like it. So it's like a unified way how to deploy different models on Kubernetes, and they provide a bunch of different metrics. So for us, the deal is just to add some clever auto-scaling. Because, for example, if you are scaling out the models and you have an open session with the model and you are prompting the model, you would like to end up with the request on the same replica, or in the replica that has the cache already present, because you don't want to reload the whole conversation. So there are some tricky things about the serving and the auto-scaling part of the models. But luckily, there are some clever people thinking about this already, so not me. So this is something that will be handled pretty soon. Okay, so this was like a overview of what auto-scaling can do for us. And now we'll talk about KEDA. KEDA is the autoscaler that allows you to scale on applications. I would like to ask, is there anyone who doesn't know what KEDA is? Okay, one guy, two guys, three, four, cool. Any users in production? Okay, bunch of them. Okay, so I will spend just a few minutes here. So with KEDA, we tried to make Kubernetes event-driven autoscaling as simple as possible. This was the initial idea behind this. We evolved into more mature state. We can scale any workload on Kubernetes based on different metrics, and we can also schedule Kubernetes jobs. There are 65, I believe now it's like 75 different event sources. The event source is the trigger for our metrics. So in the previous example, it was the Kafka, for example. There is plenty of sources you can use. I'll cover this just briefly because we don't have much time. So when we built KEDA, we wanted to use what's already present in Kubernetes. So we are internally using HPA to do the actual scaling, but we just provide a layer on top of it. We have a bunch of resources where you can define the scaling, scaled object, scaled job. I will cover this briefly. And KEDA basically opens the connection to the target service, for example, the Kafka, get the metrics, and feeds them to HPA. And it also manages the scaling from 0 to 1, because as we know, HPA cannot scale to 0. So this is very, very brief overview. So one thing we can do with KEDA is we can auto-scale Kubernetes workloads. What does it mean? Instead of defining the HPA horizontal pod autoscaler resource, we define a resource which is called scaled object. And with that, we can scale any deployment, stateful set, or any custom resource that implements this scale sub-resource. It's very simple. It's just the pointer to the replicas and some fields. So it's very easy to augment your custom resource with the scale sub-resource, so you can then scale it out. And the scaled object has 3 parts. So the first part is the scale target. So in the scale target, we tell KEDA what workload we would like to scale. The second part is some configuration options. So in this case, it's like a minimum replica. So we will scale from 0 to 100. There are some additional options hidden here for brevity. And then the last important part is the trigger section. And in the trigger section, we define the metrics we would like to get. And there could be multiple different triggers. So it could be Kafka, RabbitMQ, Prometheus combined together. And we get the metrics, and based on that, we do the scaling. The second case is scheduling Kubernetes jobs with KEDA. For that, we have a resource called scale job. You can think about scale job as a cron job on steroids. So there is a standard Kubernetes job, which is like in comparison to deployment, it is a start and end. So it ends into completion. So you can create these jobs to do some specific task and end. Cron job extends Kubernetes jobs, and these jobs are running on cron schedule. So for example, every day at 5 a.m., this job is being scheduled, it processes the work, and it's done. Scale job gives us the flexibility, so we can use all the metrics that we have, all the triggers we have in KEDA, to actually dynamically schedule Kubernetes jobs. So in this case, again, RabbitMQ, we are targeting the RabbitMQ or Kafka, and the idea is very powerful. If there are some messages or some, we are doing some batch processing or something like that, we can just spin those Kubernetes jobs as we need them. And why we should do this instead of Kubernetes deployment? If the job takes a long time to actually execute, so it could be hours, maybe days, deployment wouldn't be the best case or best way how to do this, because if we use deployment and scale out through scaled object or HPA after some time, once the metric is gone, it will try to scale in again the actual deployment. But for the scale Kubernetes jobs, we can just create them as we need them based on the metrics. Okay, so this was like a KEDA in 5 minutes. And I would like to talk about some best practices running KEDA in production and et cetera, et cetera. For people that don't know stuff about KEDA, this might be still beneficial, but maybe some things will be a little bit complicated. Anyway, so one feature I would like to highlight is a fallback. So if we define scaled object and the scaled object gets some data, for example, from the Kafka, and if the Kafka is down, we cannot get the metrics, so we don't know what to do about scaling. If we define fallback, there we can define if there is a problem with the target service, let's scale out to the specific number of replicas or keep the current number of replicas, etc., etc. So it's very simple, very powerful. I definitely recommend it, especially if you are depending on services that are outside of your, let's say, influence. Second part, this is like a advanced feature. If you recall, when I was talking about scaled jobs or scaled objects, I told you that you can define multiple different triggers for the same workload. So you can define, for example, Prometheus, Kafka, RabbitMQ for the same workload, and then the default behavior of HPA is that it selects the largest value for the actual scaling decision. So it evaluates every let's say trigger, every source, and then selects the largest value for the actual scaling. So for the number of replicas there. This is good, but we would like to have some kind of flexibility here. So we will maybe not use the maximum. Maybe sometimes we would like to use the sum of the metrics or average. So for that, there are scaling modifiers where we can take every value from different trigger and evaluate it. And we can actually use mathematical formula or conditions here and have like very tricky long, let's say, formulas to actually evaluate the metric and then provide this metric to HPA. It's very powerful and it can help with the complex scenarios. One of examples, very simple one, very easy to understand, is this. This was an actual quote from a user. He asked me this question. We have this requirement to be always over provisioned by 3 pods. Our single pod can process 3 messages at a time. How can I achieve that? So the answer was simple. Let's use scaling modifiers and use the formula trigger value plus 9. Why 9? Because 3 pods and 3 messages. So every time when there is some kind of scaling, there's always like three pods on top of it. Very simple, very powerful. Now this is like a general recommendation. If you use plain HPA, always make sure to configure the scaling behavior. The scaling behavior tells HPA how it should perform the actual scaling. So how fast it should add more replicas or remove the replicas of the application. It can prevent, let's say, like this flopping, when you are constantly adding new replica and removing it. So this policies helps define this kind of behavior, both for scaling out and scaling in. If you can see, like on this screen, there is like a scale down, which should be scale in as I told you, but this is like the bug in Kubernetes, so we cannot do much about it. Okay, very very typical scenario again. One of the scalars in KEDA, it's called cron. It's very very simple. So you can define a cron schedule, and based on the cron schedule, you can do something. The typical question from new users we got is like, yeah, I would like to scale to 0 outside of working hours, and I specify the cron scalar to scale to 0, in the specific cron schedule, and it doesn't work. Yeah, it doesn't work because of the way how we provide the metrics to HPA and how HPA evaluates the metric. So the recommendation is actually to do it vice versa. So specify the workload to scale to 0 all the time, and in the cron schedule define when we would like to be at least at some amount of replicas. So think about it the other way around. Polling interval, very good stuff. So when KEDA tries to get the metrics from the target service, for example Kafka, there is polling interval. I don't know, by default maybe 30 seconds or 60 seconds, I don't know. But there we define how often should KEDA ask for a new metric. But the polling interval is used only for 0 to 1 scaling, because this is the scaling managed by KEDA. For scaling from 1 to n, it's based on the HPA. And HPA actually, under the hood, is making the calls. So it is requesting the metric from KEDA. So by default, on most Kubernetes distributions, the interval for HPA is 15 seconds. So every 15 seconds, the HPA asks for a metric for this specific workload. So then this call is propagated to KEDA, and KEDA then asks, for example, the Kafka. So then when we are talking to these kind of users, and they would like to, we would like to have like more real-time scaling, so we reuse the polling interval to very bare minimum. But eventually what they just do, they will just overload the actual service there, because they are making way too many requests. And usually they define the polling interval when the minimum replica is larger than 1. So it doesn't have any effect at all. So it is just making the pressure. So think about the polling interval, think about the scraping period, and when you are designing the solution, to not overload it. I will cover this briefly a little bit later. Yes, this is a little bit controversial. If you are a KEDA user, or maybe the introduction to KEDA is very simple usually. You are running Kubernetes, usually you have your Prometheus stack there. And based on the stuff I just told you in the previous couple of minutes, Prometheus provides you some custom metrics. So let's use these metrics for autoscaling. That's very simple, very good idea actually. There is a scaler in KEDA that talks to Prometheus, very powerful. But there are some gotchas in here. So for small setups, it's perfect solution. So for a lot of cases, it's a very perfect solution. We have the metrics there in Prometheus, or maybe it's Datadog or Dynatrace or any other metric source. So let's use it for autoscaling. If you are running the, let's say, small setup, small cluster, or you don't need to have, let's say, real-time metrics, so you can really like extend the, the period when you are requesting the metrics, it's perfect. But once you are starting actually scaling out the whole infrastructure and the whole setup, and you have like hundreds of workloads on a single cluster or multiple clusters, and all of them are talking to the same Prometheus instance somewhere, you are making way too many calls there, because every 15 seconds HPA asks for a metric. On top of that, there is this polling interval. So this could be, and this was very common question I got from users. It was like they have like a polling interval set to 1 second. They have like hundreds of scaled objects, and Prometheus wasn't able to respond. So they have a lot of outages there, and scaling wasn't happening. So this is the problem in the nature of the whole setup, because the first you overload the Prometheus. The second problem is that there are two scraping periods, two intervals that are added there. So first interval is from the workload to Prometheus. So first Prometheus needs to scrape those metrics. I don't know, it could be 30 seconds. And then KEDA needs to again scrape those metrics. So if you have like this, real-time workloads, this wouldn't work, because you will reduce the intervals, and then you will start hitting the problems there. Also, sometimes the Prometheus is outside of your Kubernetes cluster. It's maybe one managed instance. So you are making a lot of unnecessary calls outside of the cluster. So you might be actually paying for this, sometimes cross-zone traffic, or out of the cluster. So it could actually cost you a lot of money. Or if you don't use Prometheus, use Datadog. You might start hitting a rate limit from Datadog if you don't pay them a lot of money to have like some extra tier. So this could be also tricky. So I'm not saying Prometheus metrics are bad. So you should also always be, always think about this problem, and try to use different kind of metrics or different setups. in this case to overload this or overcome this problem.
Quick question.
Mm-hmm.
Since Prometheus is essentially tool-based, meaning that Prometheus is scraping the endpoint, is there something preventing the scaler to actually scrape the endpoint directly so that you can get away with one of those?
Yes, actually, this is like the recommendation. It's tricky to do this like directly from the Prometheus because in the you are not getting just the metric from the workload, but usually it's like it's Prometheus query. So you have like some kind of average over 5 minutes, or you are yeah. So then it's tricky. At KEDA we have a solution for this. We are utilizing OpenTelemetry actually, and we are getting the metrics directly from the workload. But this is something you should think about. I'm not saying it's bad. So if you are happy with Prometheus, use it. But if you are in a certain scale, the problems will happen. Yeah, this is related. So lot of scaled objects overloading infrastructure. So think about the whole problem. Okay, so what's next for the whole scaling stuff? Predictive scaling is a topic. So if we are getting all these metrics for the workloads, why don't we use this knowledge to actually? Okay, so this is right. So why don't we use the actual knowledge and try to be more proactive actually? So the idea is to get all the metrics that we are getting them, feed them into some time series model, like Prophet, and try to predict the actual load. This is a very good solution for workloads that have like some kind of periodic loads, some kind of repetitive load coming to the service. So we can, in this case, with the predictive scaling, we can start scaling out a little bit in advance, so the application then can handle the load more gracefully. Yeah, the other stuff in the mix for the next couple of years is like how to tackle stateful workloads, because all the stuff we discussed here, you should always think about how when you are developing your applications on Kubernetes to make them really cloud native ready. What does it mean? The application should be able to start as soon as possible. So please try to avoid Java or Python, yeah, whatever. And you shouldn't store the state ideally in the application itself. So then you can really like scale out the application, or just create it or kill it, and to be ready on Kubernetes. The other let's say hot topic is like AI-driven autoscaling, because AI is like everywhere, right? So we have all these different signals, different metrics coming from different sources. So why don't we send it over to some model and to actually give us some good idea what we should then do then.
What does AI-driven autoscaling mean? I would understand machine learning-based autoscaling or predictive model-based autoscaling, but when we talk like artificial intelligence, I translate it as LLM-based autoscaling, and that does not make sense to me.
I don't know. Really don't know. But the idea is you have like these multivariant models, right? So you can send multiple different signals there, and then the AI will come up with some number. This is the answer.
Model, not AI.
Oh, this is not predictive, because the predictive it follows the trend in the metrics. So it tries to spot the actual trend in the metrics, right? But this kind of AI scaling it doesn't try to spot the trend there, but it maybe gets different signals. Yeah, exactly, and it invents the. I know it might sound funny, but I was talking to one company. They want to do something like that because their setup was really crazy and unique, and they would like to have like, it should be more like a autonomous scaling, maybe. Yeah. So yeah, whatever.
Instead of scaling based on metrics and data, you start scaling based on randomness.
I will keep you. If we will cooperate with this company, I will definitely keep you posted. I don't know at the moment yet, but maybe they don't know also what to do. And also like the last stuff. So when I was talking about scaling out GPUs, AI, LM workloads, where it actually makes sense because you would like to host those AI models and workloads on Kubernetes. There's still the stuff to be done there. So this is something we should do and cover in a few steps. I believe we are on the top of the hour, are we? I don't know. What is the time?
Yeah, fine.
Yeah, I have some appendix, but this is probably too long. Only if you are interested, I have like this chain scaling. Can you hear like 5 minutes?
Yeah, 5
Yeah.
minutes are fine, and we have a lot of questions.
Do we have more beers? So we go.
I think I got the last one.
I just want to quickly cover this. So there was like this proposal on SIG autoscaling about like some coordinated scaling. I will be very quick. So the idea was like I would like to, HPA always tries to scale. The relation is 1-to-1. So you have one HPA object or scaled object in for the workload. And in this proposal, it was like, okay, let's augment this a little bit and add more, let's say, relation to the different workloads. You can imagine as, for example, scaling out front-end and back-end application. Okay, yeah, so sorry, there's the delay. So this is like the traffic coming to our application. We have a front-end, back-end, ABC. All of them have HPA in it. So we are starting, sending the traffic there. So the front-end is busy. HPA tries to, manage the load. It starts scaling out. Sorry, the delay. Okay. We should scale out the Google Meet probably. Yeah. Yeah. So finally HPA. You can see a lot of delay there in the HPA. So it was able to scale out the pods, and then again the backend is under pressure. So again HPA will take some time. So I will click a few times and then sip beer.
Wait for autoscaler.
Yeah. So this should be like a gradual, let's say. And then finally the first front end is ready, and then gradually also the back end is ready after some time, right? Okay, so this was the proposal to the SIG autoscaling group. So let's invent new resource, next to HPA that will manage this kind of situation. There were some proposed solutions. I won't go into that, but it was like modifying the HPA API in Kubernetes. If you know something about Kubernetes caps, like the process for extended Kubernetes, you don't want to do it. It's painful. So it takes years actually to go through. Or create new resource again, like next to HPA. Again, the process would be painful. So actually, there is a solution. We can use scaled objects, and luckily in KEDA there is a Kubernetes workload trigger that can trigger that is triggered by different workload. So then the idea is really like we switch the HPAs into scaled objects here, and okay. So this is the scaled object for the first backend. It still uses the CPU utilization as before, but we added Kubernetes. Sorry, I have like also like this highlighting. I'll skip it. Anyway, so we have like this Kubernetes workload scaler that can target specific pods for different workloads. So in this case, once we start scaling out this guy, we immediately start scaling out this. So we are not like hooked, but we start scaling out this guy. So immediately the scaling is instant. I have also demo on this. I won't show you because we don't have time, but I have recorded demo in case someone is interested. So the difference was for this example case was like we went from 1 minute to 15 seconds for the whole stuff, just using the plain stuff that's in KEDA. All right, that's all from my side. Thank you very much. Ask questions.
May I ask you for a microphone?
Mm-hmm.
So we have first question, which is the condition whether a pod could be moved customizable?
That's from the
Yes. Can you target Argo workflows with scaled job?
Can we touch target Argo? You can target Argo rollouts. I'm confident. I'm not sure about Argo workflows, but if the Argo workflow CRD exposes scale subresource, we can do it.
Okay. If KEDA uses HPA under the hood, how is it achieving a more real-time scale-out than pure HPA? Is it thanks to more data sources?
Yes. is the nature of the metrics. So the HPA is getting the CPU utilization from the Kubernetes metric server, and it's more like about how we react to the metrics than the actual process.
Okay. How did the developer team end up with KEDA acronym as the name for the product?
I don't know. So the project started as a cooperation between Red Hat and Microsoft. I was at Red Hat before at the time. There were some other names. One of them was Core, I believe, and then someone smart. I don't recall who it was, but because it's Kubernetes event-driven autoscaler, so this is like the because we were trying to autoscale events. It was like how to so the original idea was how to run Azure functions on Kubernetes, because Microsoft was experimenting with Kubernetes back then, and they wanted to run Azure functions on Kubernetes, so they were able to run them, but they want to also autoscale them based on the different Azure stuff.
Okay, can you provide advice on preparing a small 1 RPS application to be featured on television channels like Bloomberg?
What? Advice on preparing? Sorry, I don't understand the question.
Me neither. Who asked it?
Yeah, it was for me.
Here you go. Ask again.
So the question is mainly like, so you have a one RPS application. It's pretty simple. It just works. But then you realize that tomorrow your application will be featured on Bloomberg. So you get a lot of traffic. Any advice on preparation to this kind of stuff?
Run, get drunk, or pray if you are into this stuff. Start, so if you are using autoscaling, then also plug autoscaling there. Try to use like the cron scaler to actually, if you know about the time when you are actually start getting the load, let's pre-warn the application. Make sure that the application is able to scale out fast, so it's cloud native ready. So no shit, no Java, Python, and similar stuff.
Java can actually start quite fast nowadays.
Okay. Yeah, but it's not about fast, but it's about startup time. So, the JVM needs to start and download the whole internet there and this kind of.
There are already some
That's not the JS.
Yeah. So maybe if you have like specific, we can take this after I can give you some advice.
Of course. Do you recommend using modifiers or change the app to emit a meaningful metric?
It depends. So if you can change the application to emit different metrics that use this, yeah.
Agree. What happens to HTTP requests in your HTTP scaler while it scales from 0 to 1?
Yeah. So the metric, so the request is cached, and we send a signal to KEDA to start scaling out. So we hold the incoming request there. Once the application is ready, we send it through.
So, if using metrics from Prometheus is bad, in quotes, what is the right way?
Find a different source of the metric, ideally. If the Prometheus is good for you, use it. If not, try to think about other solutions. We experiment with the open telemetry. So the idea is maybe to try to scrape the metrics directly from the workload.
And the last one, can't you do AI or whatever-based proactive scaling now? Can the user plug in whatever the data source model input that provides the signal for KEDA to act on?
No, but this is the one of the last slides I showed you. So this is the stuff.
That's all.
Yeah, thank you.
Under no circumstances can we use deterministic algorithms now.
Okay, that was all. Thank you.